Hello, everyone. Welcome to the Bay Area Kafka Meetup at Confluent. My name is Guozhang Wang. I'm an engineer at Confluent. And for those of you who are first time here, welcome to the group. And this is a place where the community share about the most recent development in the Apache Kafka codebase as well as a community. And also we exchange ideas about how to use Kafka and its ecosystems to build various real-time pipelining and streaming use cases. And all the past events hosted by Confluent are recorded, and you can find the past recordings on the YouTube channel. And of course, if you have any interesting ideas or topics that you want to share on this venue, please come directly to me to share your ideas, and we can put you on the schedule. Okay, so today we have two talks, one from Confluent and another one from Dropbox. The first talk will be given by my teammate Sophie and myself, and we're going to talk about the most recent improvement on the consumer rebalance protocol. Thank you. So before I start my presentation, let's show off your hands if you have ever worked with a consumer client directly. Anyone? Okay, so let's put your hands up if you have ever bumped into any rebalance issues, like it never ends, kills your performance, and have to be manually intervened. Okay, great. Seems like it's a good time to fix the issue, and you are at the right place. So for those of you who have not been working directly with a consumer internals and how the rebalance works, to start our presentation, I'm going to first briefly talk about the rebalance algorithm inside the Kafka consumer, and also why we call the current mechanism is an eager protocol. And then I will talk about some common scenarios where there will be issues with this rebalances due to the design of this protocol. And then Sophie will basically talk about its root causes and how we propose to actually solve this, the observed issues in the most recent releases of Apache Kafka. Okay, a very quick 30 seconds short history of consumers and how we evolved its design. So as we all know, in Kafka, data is organized into topics, and topics are sharded into partitions. Each partition is a append-only log, and consumers can basically read sequentially from the log. And there are also message offsets indicating the position of the consumer of what it has been read up to. And in order to achieve parallel processing, we also group the consumers into the so-called consumer groups. Whereas each instance within the consumer group is called a member. And for all the subscribed topic partitions, each of them will only be read by a single member of the group at any given time. So in order to scale out, you can easily just add more partitions into your topic and also start more members of the same group into your consumer groups, and you can actually have the horizontal scale out. And that's where we basically have this notion of rebalance, because at any given time, you need to dynamically decide that given a list of the subscribed topic partitions and a list of the members in your group, what partitions should be assigned to what members, right? We call it the assignment information. And since the members as well as the topic partition resources can change, this information is dynamic, means that we basically have to recalculate this assignment whenever things change. And in addition, whenever there is basically a move around of the owned partitions from one consumer to another, we basically also have to remember the offsets, the consumption offsets of the old consumers, so that when it actually migrates from one consumer to another one, the new consumer can actually picks up this consumption offset and resumes from that position. So in the old versions of Kafka, we actually put both of those information, the assignment as well as the offsets, into Zookeeper. And in Kafka 09, we basically removed this Zookeeper dependency and basically moved this information into the broker itself. To be more specific, we actually add a new module called the group coordinator on the broker side, where all the members of the same group will interact with the same coordinator to determine the assignment from the partitions to the members, as well as reading and also storing the offsets to the group coordinator. And in this presentation, I'm going to only focus on the assignment part of this protocol, where we basically use the rebalance algorithm to decide dynamically whenever things change, what partitions to be assigned to which consumer member of the group. Okay, closer look into the rebalance protocol. And first of all, when we should actually trigger a rebalance, right? As I mentioned, the rebalance can be triggered whenever there are anything changed to either the membership as well as to the resource of the topic partitions. For example, when new members or new consumer instances are started within the group, then a rebalance will be triggered. And similarly, when existing consumers are shutting down or they are crashed, the rebalance should also change, basically move their partitions to the existing members. And similarly, when the subscribed topics has new partitions added, or new topics are created, or old topics being deleted, the rebalance would also be triggered to basically reassign the newly added resources to the existing members, or to revoke those non-existing resources from the consumers as well. So to just give you an example on the membership change that triggers a rebalance. First, let's talk about how we actually detect such membership change. The first concept that we are having here is a heartbeat protocol. Whenever a consumer is under normal processing, it will periodically send those heartbeat requests to the broker side group coordinator. And whenever the coordinator receives the request, it will basically respond to that heartbeat, indicating that it has received the heartbeat. And as long as those heartbeats are periodically sent to the brokers, the coordinator basically will treat those consumers as still alive and be part of the group still. Now, suppose one of the consumers in the group, let's say consumer 2, has crashed due to some errors. Then, after some time, that the heartbeat has not been received to the brokers, broker will eventually treat this consumer as failed and then trigger a rebalance in order to move its own partitions to other members of the group. And this period of time when the brokers will treat a consumer as failed is called the session timeout. That is actually configurable on the broker side. So the shorter you configure your values, it will be more sensitive to detect such consumer failures, but also it can maybe have a higher chance to give you false positives. That if the consumer has just a soft failure, does not send you the heartbeat in time, it will also be treated as failure and trigger the rebalance. And similarly, if the consumer is gracefully shutting down, right? In order to actually notify the group coordinator sooner than later that membership has changed and a rebalance need to be triggered, it will actually send a new types of request called the leave group request, right at the point when it's shutting down. And whenever the leave group request is received, the group coordinator will basically treat this consumer as leaving the group and no longer alive, and then trigger the rebalance as well. When new consumer members are starting up, they will also send new types of requests. So basically, the protocol is the following. Whenever a consumer is starting up for the first time, the first thing it does is to send a join group request, including its subscriptions to the group coordinator. And if the group coordinator does not recognize this consumer, basically it means that it's new to this group, it knows that a rebalance needs to be triggered in order to move some existing partitions into this new member to allow it to fetch and start some work. And similarly, if the subscription of the existing consumer members also changes, like for example, in your code, you basically unsubscribe your topics and then resubscribe to some new topics, right? The existing consumer can also send a new join group request to the coordinator, indicating the change of the subscription. In this case, the rebalance will also be triggered to basically rebalance the new subscription partitions into the existing members of the group. So that's how we basically detect membership change and basically trigger our rebalance. Next is how we actually execute the rebalance. The execution of the rebalance basically is done in two phases of round trips, including the join group requests. So first of all, we basically collect all the members as well as their subscriptions into the new generation of the group. And then we select a new leader from this group to basically execute the assignment logic. And after that, the group coordinator can be used to basically propagate the determined assignment back to all the members of the group. So here is another example of the execution of the rebalance. Again, let's use the new member joining the group as a concrete example here. the join group request is triggered, is received, and the rebalance is triggered. The first thing that the group coordinator needs to do whenever it decides to trigger a rebalance is to request all the existing consumers to basically rejoin the group. And to do that, it basically uses a heartbeat protocol to encode a special error code into their response, asking the existing consumers to basically rejoin the group. And upon receiving this special error code, the existing consumers will first revoke all of their currently owned partitions and trigger the corresponding callbacks to basically do the revocation. So for example, if your consumer client is doing some heavy processing, which is like a stateful processing, you can basically leverage on those callbacks to shut down your states and checkpoint your current status as well. And after that, you see that all the existing consumers will basically give up all the partitions that they currently own, and none of them basically will process any new data. And then they will send their join group request to the group coordinator. At that point, we say that a new group has been formed where we have a synchronization barrier, because after this point of time, we know that all the members have joined the new generation of the group, and the new generation now have 3 members instead of 2. And also on the broker side, we have a rebalance timeout config, basically controls how long we should actually wait for all the existing consumers to resend their join group requests. And again, after the synchronization barrier has been set, if there's a new or existing join group request received, they will not be considered as members of this generation, but only be considered as the next generation of the group as well. So after the synchronization barrier, we have all the members that we need, and also their subscription information. We will use a second round trip to basically decide the assignment of those subscription partitions. First thing is that we will choose one of the consumer members as a leader of the current generation of the group. For example, let's say we choose C1 as a leader. We will send the response of join group request to those members, but the one that we send to C1 as a leader will be different, because in addition to indicating that you are now part of the group already, we also basically include all the subscriptions from the member to the leader to let the leader to execute the assignment logic. For the other non-leader members, right after they receive the join group response, they can now send the sync group request in the second round trip, basically to request for the new assignment to themselves. Whereas the leader, upon receiving the join group response, now need to execute the assignment logic, which is again an interface that can be customizable by the user. And let's say in this example, the leader decides to basically give one partition from each of the existing consumers, C1 and C2, to the new member, C3, namely partitions 3 and 6. And after it had done this assignment, it can now send this assignment as a whole in its own encoded sync group request to the group coordinator. And then the group coordinator can basically propagate this assignment to each one of the members. And after receiving this response, the members will now assign those partitions back to themselves and trigger the other callback, namely the on-partitions assigned to, for example, reinitialize your states for your processing, and then normally process your data after you have assigned those partitions. Okay, so this is a quick recap of the current protocol of the rebalance. As you can see here, we basically allow users to basically customize the rebalance protocol by both like customizing the partition assigner, which basically executes assign functions, as well as the rebalance listener, which basically executes the on-partitions revoke and assign callbacks in order to basically initialize or shut down their processing logic as processing state. And from Apache Kafka, we have a couple of built-in out-of-the-box assigners, such as the round robin and the range, and also sticky assigner, which basically tries to give back the partitions to their original owners of the members whenever a rebalance is triggered, like what the example I showed you. And also in higher level clients like Kafka Streams, we also have its own implementation of the partition assigner, like the Streams assigner, which basically does similar things, but also to leverage on the assigner and also the callback to basically handle some stateful operations as well. So this is like a very straightforward rebalance protocol. But what are the problems with this protocol? Well, it's mainly in two folds. Number one, it is basically a stop the world protocol. Because whenever everyone is joining the rebalance phase, they have to basically give up all the works at hand, right? This is like indicated by the purple bar at the beginning of the rebalance. And then at the end of the rebalance, they may get some of the partitions back. So during this phase of two purple bars, basically your throughput of consumption basically drops to 0. But if you are using, like in practice, a sticky assigner, for example, you will observe that in most cases, you basically give up all of your partitions, and then at the end, you will actually take back most of those partitions if you are using sticky assigner. So what you will observe is that because of this eager or like stop the world protocol, you basically is wasting a lot of resources during the rebalance, as well as not processing any data at all during this phase of the time. And the second issue with the eager protocol is that it always tries to trigger the rebalance immediately and always tries to shuffle all the partitions among all the members at a given time. And another common scenario we can see here is whenever you are trying to bounce an instance of your member. For example, you first try to shut down the member, which will trigger one rebalance. And then right after the shutdown is finished, but before the rebalance is completed, maybe that instance has been resumed, and which will also trigger another rebalance. And during those rebalances, because your callback may take time and your assign algorithm may take time, they will also actually have a storm of rebalances if they have timed out. And you will basically observe that whenever you are doing those operations, you will see this so-called endless rebalances that actually takes a very long time. But what it really does is to just shuffle the partitions around, and they actually are not doing something like meaningful, because whenever an instance is bounced, you are giving its partitions to other existing members, later on only to give them back to this resumed partition, resumed members. Which is also actually a long waste of time because of this eager design of the protocol as well. So that is like what we have observed so far. And I will now hand it over to Sophie to discuss about its root cause and our approaches trying to tackle it.
Thanks. Cool, yeah. So let's quickly revisit when we want to actually trigger a rebalance, who participates in the rebalance, and what actually gets reassigned. So with the current protocol, the eager protocol, the when is immediately, the who is everyone, and the what is everything. So basically, everyone has to give up everything immediately. And as Gojang pointed out, this is pretty wasteful in a number of ways. First of all, we might have a rebalance when we don't really need to, such as when you've just bounced an instance and it's going to come back. And also, it's wasteful for everyone to have to give up all of their partitions and stop working on them, since in many cases, after the rebalance, they will just have most of their original partitions reassigned back to them. So if we were to think about what the ideal protocol would look like, well, first, the when would be, of course, only after we've determined that something actually needs to be reassigned. The who would be only the consumers whose assignment actually needs to change. And of those consumers who need to change their assignment, of course, only the partitions that actually need to change ownership. Of course, in order to have overall balance across the cluster. So this is our proposed protocol, which we call the Incremental Cooperative Protocol. And this has actually been addressed in a number of KIPs. So just briefly, it's kind of broken up into connect and the consumer and streams, which is built on top of the consumer. I'll refer you to KIP 415 or the Kafka Summit SF talk for the details on the connect incremental rebalancing. And then just briefly, KIP 345, static membership, addresses the when. So basically, it helps prevent needless rebalances in the case of a member that briefly leaves and then immediately comes back. And there was a previous Meetup talk on that, which I'll refer you to. And then lastly, we have KIP 429, which is the focus of this talk, which is the incremental rebalance protocol in consumer and streams. So just to take like the consumer's view of this, we have the set of own partitions. So this is just what we call the partitions, the assignment before the rebalance, basically. And on the other side, we have the assigned partitions, which is the partitions after the rebalance, or the newly assigned partitions. So for a given consumer, then of course we have this intersection in the middle, which is the unchanged partitions. And depending on which assigner you use, if you use the sticky assigner or if you have a streams app, which has its own sticky assigner, this unchanged partitions intersection is going to be pretty large. So in the eager protocol, this is all the partitions that need to be revoked and then immediately reassigned, which can be a lot of overhead if you're committing offsets, flushing and closing, reopening stores, things like that. So then, of course, on the other side, we have the owned partitions minus the assigned partitions, which are the partitions that actually need to be revoked. So there's some subset of partitions that we actually do want to migrate to a different consumer. Otherwise, we wouldn't be rebalancing. And we want to only invoke this callback on that subset. And then, of course, on the other side, we have the newly added partitions, which is the assigned partitions minus the owned partitions. And again, we only want to invoke this callback on that subset. So that's all pretty obvious. And honestly, that's kind of how I thought it worked before I knew anything about the consumer group protocol. But there's a few challenges in order to kind of implement this smarter assignment. So first of all, there's the issue that, well, we don't really know the owned partitions and the assigned partitions at the same time with the current protocol, right? The owned partitions is the before the rebalance, and the assigned partitions is generated by the rebalance. So we don't really have that information at once, and so we can't really generate these separate subsets with the current protocol. And then the other challenge, which is what the eager protocol was really aiming to address, is how to do this safely. So Gojong mentioned, we only have one consumer reading from a partition at any time, and this is really a strict requirement. So we don't ever want to have any partition that has two consumers that think they own it at the same time. Otherwise, you might have all kinds of data corruption. So in terms of like an actual constraint, what that translates into is we want to make sure that for any given partition, we always invoke on partitions revoked for it before on partitions assigned is invoked for any consumer. So how do we actually do that? So let's go back to this scenario that we were looking at before, where we have two consumers, they've each got 3 partitions, and this new guy, C3, joins the group. So he sends his join group, the broker responds with the heartbeat response, and now C1 and C2 know they need to rejoin the group. So in the eager case, they would immediately revoke all of their partitions before setting the join group. But obviously, we want to try to avoid this needless shuffling and revoking of resources. So we want to try to just hang on to them for as long as we can. So in this case, let's just try sending the join group with all of our own partitions still owned. And we send the information about which partitions we own in our join group request. So the broker collects all that information and sends it back to basically to the leader. And the leader generates the assignment based on the assigner that's embedded. So in this case, let's say we have a sticky assigner, and the assigner does its best to give back partitions to the original owners. But in order to achieve overall balance, we have to actually give away 2 of these partitions. So it turns out that C1 and C2 actually need to be revoked from, partitions 3 and 6 need to be revoked from C1 and C2 before they can be given to C3. So the assigner knows that we need to enforce this revoking partitions before reassigning them restraint. And so what it does is it says, okay, well, we'll tell C1 and C2 to revoke these partitions, but we won't yet give them away to C3. We don't want to introduce a race condition where C3 might call on partitions assigned before these have actually effectively been revoked. So C3 ends up just getting back an empty assignment, and everyone sends their sync group, and the broker sends everyone their new assignment. So now C1 and C2 notice, well, we each have to call on partitions revoked, but only on one partition. Instead of all 3, we just figure out, based on our new assignment and our old assignment, there's only one partition each. So we revoke that single partition, and then we notice that because we had to revoke this, we assume that these partitions are actually not yet assigned to any consumer. So at this point, partitions 3 and 6 don't really have an assignment. They're just floating in purgatory. And C1 and C2 know, because they had to revoke that, that they should trigger another rebalance so that these extra partitions can be finally reassigned to their final owner. And C3 doesn't have to do anything because it doesn't have any partitions yet. But C1 and C2 send a join group and trigger a new rebalance. So they rejoin the group, again, holding on to all their own partitions. And we're, again, at this point where we want to generate a new assignment. So we call the assign method again. Hopefully, we're using a sticky assigner. And if we are, it should generate the same assignment, except now partitions 3 and 6 have already been revoked. So there's no partitions that need to be revoked at this point, which means we can safely give them away to C3 right away. So we generate the new assignment, send it back, and everyone gets their new assignment. And only C3 actually has anything to do at this point because it needs to call on partitions assigned on 3 and 6. But C1 and C2 have nothing to do because their assignment hasn't changed. So everyone can just happily go on processing. Right, so that's the cooperative protocol. You'll notice that we actually make this trade-off where we trigger a second rebalance, whereas normally there would have only been one. So the overall goal of this, of course, is that rebalances should be cheaper, they should have less overhead, and they shouldn't stop the world. So we think it's reasonable to trigger a second rebalance if they're going to be much more lightweight. Notice also that we have to make assumptions about the assigner itself. So this really works best if you have a sticky assigner. If your assigner is generating a random assignment at each rebalance, then you're going to have to revoke probably a large subset of your overall partitions, and this kind of regresses to the eager protocol at that point. And since each consumer is actually holding on to all their partitions at this point throughout the rebalance, they can actually continue to fetch during the rebalance and can keep processing whichever partitions that they own right up to the point where they potentially have to call on partitions revoked and give them away to someone else. So between the purple bars at this point, you'll notice that C1 and C2 can happily continue processing partitions 1, 2, 4, and 5. All right, so we did some benchmarks. We used a streams app, a stateful streams app. So by that we just mean it has some embedded state stores, has a lot of resources that it has to manage. So things like on partitions revoked are kind of a heavy call for it to make, especially if it's flushing or closing and reopening a store unnecessarily. So we tested this with a rolling bounce with 10 instances. And you can see where that happens because on the right there, which is the eager protocol side, the throughput drops pretty much immediately to 0. And this continues pretty low rate up until the rolling bounce has completed and the group stabilizes, and then it can return to its usual throughput levels. But then on the left, you'll see that the cooperative protocol, it has a slight dip. There is some overhead still with regards to rebalance. But for the most part, it can continue actually processing during this rebalance time or during this rolling bounce. And so it's really not quite the stop the world effect that it used to be. So in terms of measurements, we measured the overall time that these instances were just sitting there unable to process during the rebalance. And we saw about over a 10%, order of magnitude, 10 times reduction in the total time spent paused. So it's pretty nice. Okay, so in terms of how do we actually do this, or how can you do this in your own app? We augmented this Assigner interface. First of all, we added we include the own partitions in the subscription. So basically, the Assigner now has the information of all the own partitions for every member. And it can use that to try to be as sticky as possible and to try to give back all the partitions to their previous owners. And it can also use that, of course, to figure out which partitions have to be revoked first before they can be reassigned. And then we also added this supported protocols method, which basically the assigner just uses to indicate if it only supports eager or if it also supports the cooperative as well. So we have this usual built-in assigners, the range, round robin, and the sticky. These all just continues to support only eager. And we actually added a new assigner out of the box, which is the sticky cooperative, which, as the name suggests, supports the cooperative protocol. But it follows the same algorithm as the usual sticky assigner. And then, of course, there's custom assigners, so you can implement your own. We would recommend, of course, making it as sticky as possible if you want to support the cooperative. And in the case of the streams assigner, you have a Streams app, it will actually support both eager and cooperative. In addition, we actually augmented the consumer rebalance listener, and there's some semantic changes to how these callbacks are invoked. So previously, on partitions revoked would just be invoked at the beginning on all the partitions, and the opposite for on partitions assigned. But with the cooperative protocol, on partitions revoked will be invoked at the end of the rebalance and only on what actually needs to be revoked. And furthermore, it will actually not be invoked at all if there's nothing to revoke. Then on partitions assigned, similarly, is invoked at the end only on the partitions that are newly assigned. But unlike on partitions revoked, this will always be invoked just so you can, just as a way to indicate that a rebalance is just completed. So then lastly, we actually added a new callback, on partitions lost, which is meant to tackle a longstanding issue where a member falls out of the group. So a member, they might be stuck doing some heavy processing or a GC pause or something and somehow miss a whole rebalance. So after that missed rebalance, it actually, all of its partitions have been given away to other consumers and it no longer actually owns any of the partitions that it thinks it owns. So in the eager protocol case, what would happen is when it notices that it's fallen out of the group, it goes to rejoin the group and it would call on partitions revoked on all of its partitions. So on partitions revoked typically involves things like committing offsets, which of course, if you don't actually own that partition is doomed to fail. So we added this new callback so that if you actually fall out of the group, you can avoid things like committing offsets or other actions that require ownership of the partition, and just do any other resource management that you might want to do, like closing a store or flushing it or anything like that. All right, so cool. So now we want to talk about how do you actually switch over to cooperative rebalancing? How do you upgrade safely? So you have to follow a specific upgrade path in order to do this safely. It does differ between if you just have a plain consumer app or if you were using streams. But the same idea applies where you have to do 2 rolling bounces. And in the first rolling bounce, you effectively turn off cooperative protocol and you upgrade the bytecode. And then in the second rolling bounce, all you have to do is just turn on the cooperative rebalancing again. And the details differ, and I would refer you to the KIP, or you can ask us later. But it's important to note why this is necessary. So just to illustrate this, imagine you have a Streams app on 2.3, and you just want to blindly upgrade using a single rolling bounce. The problem there is, of course, let's say you're halfway through the bounce, and half the members are on the new bytecode and following the cooperative protocol. Well, when a rebalance is triggered, all those members would not give up any of their partitions. They wouldn't call on partitions revoked on any of their partitions before joining the group. Whereas, of course, all the eager members would revoke everything. So the problem is if the leader then is chosen from one of the members on the old bytecode, it has this assumption that everyone has revoked all of the partitions. And therefore, it thinks it's safe to reassign any of these partitions. And of course, it will just give away a bunch of partitions that have never actually been revoked yet. And you introduce a race condition where you might have 2 consumers who think they own a partition at the same time. So it's important that you follow this specific upgrade path so that the leader ends up being chosen from someone on the new bytecode and knows how to handle both the eager and cooperative protocols. Cool. Okay, so I'll just leave you with a few takeaways. So basically, the goal was we want to extend the rebalance protocol to be smarter about how it assigns and when it triggers a rebalance. So KIP 429 really is targeted at the who and the what, so that only what actually needs to be shuffled around ends up being involved in the rebalance. And what that means is consumers can retain ownership of their partitions during the rebalance, which means they can keep processing them, and we no longer have to stop the world and rebalance potentially for no real reason at all. All right, thank you. That's it. Well, I guess we'll take your questions now, and you can contact us here.
Any questions?
Well, I don't need a microphone. But what version of Kafka do we have to run to implement this feature? Like 2.4? Which? Yeah,
you mean like the client or broker?
Broker.
It should be compatible with all broker versions.
Yeah, so so for this specific kit, which is 429, we didn't make any changes on the broker side, which means that it's compatible with broker. For the other two that we mentioned, for 415, which is static membership, that indeed have a implementation change on the broker side, which means that you have to upgrade your broker as well. But for this one, we just talk about you don't need to upgrade your brokers.
But clients, do they need a different version?
Yeah, so the clients need to be on 2.4 to support the cooperative.
So between the revocation and the reassignment, you got partitions in your example 3 and 6 that have yet to be assigned, right? What's the behavior when somebody's looking for those partitions in particular?
You be more specific? Like, what do you mean looking for?
Yeah, if somebody's looking for that information, is it available at all?
Like which partitions haven't been reassigned?
Yeah.
Oh, I see what you mean. Yeah, I think you could probably figure that out from the logs. Possibly debug logs, but yeah, I mean, it shouldn't really matter, hopefully, but yeah.
So in the beginning of the talk, you mentioned there are some known issue for the constant rebalancing for either Kafka streams or the Kafka consumer. So I'm wondering if you can explain a little bit about what's the potential root cause of that. Why would that happen for the current rebalancing protocol?
So why would we be stuck rebalancing?
Yes.
And part of that was largely due to, like, you have unnecessary rebalances. For example, doing a rolling bounce, we have an instance go down and then come back up, and the state is the same at the end. But you have this like shuffling around of resources, and then if one member, for example, is somehow misses one of those rebalances because it was stuck or is processing heavily, then it would rejoin at the end and trigger a new rebalance. So part of that, I think KIP 345, the static membership, is more targeted at preventing unnecessary rebalances. 429 is more aimed at making them lightweight and ultimately like having little overhead so that you can keep processing during the rebalance.
Any more questions?
Yeah, one question. I haven't actually looked at the two kits, but can you mix static membership and incremental cooperative rebalancing so that you get the best of both worlds?
Yeah. Oh, can you mix static membership and incremental rebalancing? And the answer is yes. Yeah, so at that point, you should be cutting down on the number of unnecessary rebalances, and the rebalances themselves should be a lot more lightweight. So you should be in good shape. But of course,
putting another way, 415 is trying to reduce the number of rebalances, and 429 is trying to put the rebalance put each rebalance to be much cheaper. But you can definitely combine the two to basically have the both effects of the improvements.
he means 345.
Yeah, 345. Sorry. Okay, I think we want to thank you. Thank Sophie for the presentation again. Thank you. Thank you myself. Okay, the next talk we will have Richie and Kang from Dropbox to talk about their use case of Kafka.
Hello everyone, I'm Richie and this is my colleague Pang. We are from Dropbox, and at Dropbox our team owns message transfer pipeline and data processing platform powered by Kafka and Spark respectively. Today, we're going to talk about how we achieved a highly reliable message transfer pipeline at Dropbox with very low operational cost. Before that, who we are, Dropbox is a leading cloud file storage service provider. We recently introduced new Dropbox, which is our smart workspace powered by AI and machine learning to organize your content, connect your tools, and bring everyone together wherever you are. If you want to learn more about new Dropbox, you can go follow below links and you will learn much richer information about new Dropbox. So what we're going to cover today, first we're going to go over the use cases that we have where we use Kafka as an event streaming platform. We'll go briefly over the configurations, the scale at which we are operating, and some of the trade-offs we made on the way on the features. Then we will look at the challenges that we had in supporting our clusters at that scale and the work we did to mitigate them. Cool. So from the use case perspective, we can broadly classify the use case as the ones which require async producers and the others which require sync producers. So data analytics is one of our biggest use case for async producers. We have around 60,000 plus machines which produces logs at the rate of 7 to 8 million messages per second. And all these logs need to be stored somewhere for further analysis. Kafka is at the heart of this data analytics pipeline. Apart from Kafka, we also have goscribe, which is an inspiration from Scribe from Facebook, but completely redesigned and restructured to suit Dropbox infrastructure. However, the main idea is clients produce logs asynchronously to goscribe, which is a global service hosted on all of our production machines. The goscribe leaves then send messages to goscribe aggregator, which is the next tier. And here, as the name suggests, the messages are aggregated over the same set of topics. And then goscribe aggregators then talk to Kafka. This reduces the number of connections that is going to Kafka very dramatically. On the other end, we have Kafka Connect, which pulls the message from Kafka and puts it into Hive. We also have other consumers who are consuming from Kafka, streaming from Kafka for real-time processing. For such use cases, we provide SLA, availability SLA of 3 nines and durability SLA of also 3 nines. The other set of use cases are sync use cases where client needs to know whether the message reached to Kafka or not, and they can take an action based on that. Some of the use cases around sync are our search indexing pipeline, campaigns notifications, or a job queue for CAPE, which is our in-house ultra-low latency real-time processing platform. In these cases, the clients talk directly to Kafka and also consumes directly from Kafka. As you can imagine, these requires high durability, so we provide availability SLA of 3 nines and durability SLA of 4 nines. Note here, our SLO is still much higher than 4 nines, but there are scenarios where we have to, during the outages, we have to do unclean leader election, and there's a possibility of data loss. So we do not support as an SLA more than 4 nines here. We have other systems at Dropbox which provide much higher durability guarantees with other costs, and the idea is we recommend our users to choose the right system based on their use cases. So let's quickly look about the configuration and scale. Currently, we are at Kafka version 0.10.2.1. It's pretty old. I acknowledge that fact. But we are moving to 1.1 soon. We have a mix of hardware rate and software rate. And the general configuration at a high level is replication is 3 and min ISR is 2. We use Go and Python clients. For scale, we are operating more than 40 clusters today with more than 400 brokers. They are producing messages at the rate of 15 million messages per second, and their average produced latency is less than 10 milliseconds. So let's quickly talk about the features that we support and that we do not support. So the first feature that we do not support is keyed messages. That is, we do not allow our users to dictate which partition the message should go. This is a conscious decision we took in favor of high availability. There are many times when you have to internally increase the partitions because your partition cannot handle the traffic or your partitions are offline. And to provide the high availability, we just increase the partitions internally. The idea is in such scenarios, neither the users should be affected, neither we should have too much of work around that. So we automated this whole process to make sure that partitions are increased automatically during these scenarios. This, of course, means that we cannot support ordering, so we do not support ordering of messages. And last but not the least, we support at least once message delivery. That means your users need to be, use cases need to be idempotent. So we have heard about war stories if you have gone to summits and all that. So this is our war story, how we achieved high reliability. So our formal team did a pretty good job in setting up the cluster, onboarding the use cases, making sure that we can have messages at like 10 million messages per second per cluster. but operationally it was pretty heavy. We were 4-people team, and our 80% of our engineering time was just running the service smoothly. This is not a very good state to be at. So past year we spent dedicated time to fix our infrastructure, and today we are spending less than 10% of our engineering time to run these clusters smoothly. So let's talk about what challenges we had. Of course, these set of challenges will not cover everything, but I believe, at least from our side, this has the highest impact. So let's start with the clients. The first thing was our clients were not robust enough. What does that mean? Whenever we did any maintenance operations, our clients either see high produce latency or lots of failures, which were not acceptable for our use cases. One of the things that we noticed is, even though we do not support keyed messages, whenever a client chooses that this message needs to be sent to this partition, after that, if that fails and the retries happens, it used to send to the same partition. So if your partition is offline, you will, even if you do number of retries, it will be still unsuccessful. Or even if that partition comes online after a while, you will have high produce latency. So internally, we tweaked this algorithm to make sure that when the retries happens, it also happens to a different partition, but and also on a healthy partition. And we determine what healthy partition is based on timeouts. And if you cannot find a healthy partition, then the failures should be fast so that we can correspondingly do better on the client side. Next is long and dangerous maintenance operations. So initially, when we have all these use cases, we were allowing people to have retention up to 12 days. Our cluster sizes were greater than 40 brokers. Messages can go up to 15 megabytes. All these contributed to a fact that whenever you have to do some maintenance operations like rolling restart or broker replacement or adding a broker, it used to take days to do that. So basically, you are taking days to reach a cluster to a healthy state. And this was specifically problematic if you have outages. If you have outage and you have to do one of these operations, and then you know that it will be days to get again to a healthy state. So we have strict policies around what can be supported by the system and what cannot. We do not support more than 3 days of data retention on our clusters. Message sizes should be less than 1 megabytes, and our cluster size is less than 15. And the cluster size is less than 15 because in many situations, if there's an outage, the brokers will observe an unclean shutdown, and which takes longer to bring the broker up. And we want to make sure that in such scenarios, if you restart your whole cluster, it should be within 30 minutes of duration. So that is the reasoning around the 15 brokers. Next, insufficient understanding of failure scenarios. If you do not understand your system, what it can support and what it cannot support, you are just running blind. We made sure that we have completely automated DRTs that we run, which are run regularly, like rolling restart, like introducing chaos by yourself at regular intervals so that you understand your system. And these are automated. It sends us the report at the end saying, this is failure, this is not a failure, and we can take actions accordingly. This helps us to catch the problems more proactively rather than during the time of outage, and also helps to build a confidence in the system to tell our clients what to do and what not to do. Okay. The next two are the ones which we are gonna deep dive a little bit more because it's some architectural changes that we made. First is keeping up with organic cluster growth. So now you have the cluster, your use cases are onboarded. No one is gonna tell you that I'm gonna increase my traffic. No one is gonna tell you that, oh, this particular date to this particular date, my traffic will rise so and so. So how to cope with that? There are two different types of organic growths. One is topic level and one is at the broker level. So at the topic level, you can increase the number of partitions. Say when traffic increases, you have to increase the number of partitions. Or if your partition reaches to a certain size, you have to again increase the partition so that you do not have you do not cause into risk condition of, oh, the disk has failed, now what to do. So to cope with that problem, we created a bot which continuously monitors our partitions. When it monitors, it tells us, it automatically also identifies that how many partitions are needed, extra partitions are needed if you are reaching to a certain thresholds. it sends a diff to our on-call, and the on-call has the choice to either accept that diff or it can reject the diff if it knows that, okay, this is a temporary thing and we do not need to do it. And after that, the diff is accepted, the bot automatically updates the partitions and nothing else needs to be done as a manual intervention. The second is increasing the brokers itself for a cluster. And this you cannot do if you do not know the limits of Kafka. So we created a stress testing platform which runs like tons of test cases and identify what are the limits of Kafka on a particular setup. So Pang is going to go in more detail about the stress testing platform and how we did that. And finally, handling the cluster outage. Even if you have so many guardrails around it, even if you run DRTs, things will happen. Machines will break, you will get into some issue where you do not know how to fix it, and it will take time for you to figure out what is the reasoning and fix it. So we want to make sure that during this time, so we actually got stuck into one of the outage where a broker observed a race condition internally. We couldn't figure it out. It took us 3 days to fix the whole cluster with billions of messages lost. So in order that next time we do not have this issue, we created 3 different solutions. One is for our async pipeline, which is sharding, which is a cluster level fault tolerance, and emergency failover and dynamic failover for our sync cases. Pang will go over in more details about our stress testing platform and all the 3 solutions that we just talked about.
Test. Good. Test. Cool. Now it sounds gloriously. All right. So for the second part of this talk, I'm gonna. All right. Cool. For the second part of this talk, I'm gonna cover a few of the highlights that we did in the past year that helped us combat those challenges. As Yuchi has mentioned, we built this automated stress tester that helped us to find the throughput limits of our Kafka clusters. And for asynchronous data pipeline, we actually re-architected the whole system so that we're able to scale up by sharding the clusters. And for those synchronous use cases, we implemented those emergency failover mechanisms so that we're able to respond to those failure and disasters in a much faster way. And finally, I'm going to talk briefly about our vision to the future of Kafka serving at Dropbox. First, start with the automated stress testing. Like Yuchi has mentioned, in order to cope with the organic traffic growth, we need to know when do we need to scale up the Kafka cluster, and that in turn requires us to know what are the limits of the brokers inside our infrastructure. So with that in mind, we built this automated stress tester. Basically, it achieves the goal by performing hundreds of unsupervised stress testings on our Kafka clusters. And with those results, we were actually able to make the policy for us so that we can know when to scale up the cluster. This auto tester has actually become a very valuable asset to the team because going forward, it actually has become a part of the standard procedure whenever we want to verify new hardware for our brokers, new version of Kafka, new setup with the configuration, etc. We even wrote a tech blog about this, and here's the link. And I hope later we can distribute this slide so you guys, if you are interested, you can just follow the link and see detail about that. So here's the setup of the tester. It's very simple. On the left, we use Spark to host all the Kafka clients so that we're able to generate the testing traffic in almost arbitrary scale. And on the right, we prepared 3 Kafka clusters with different sizes. One with 5 brokers, one with 10 brokers, and another with 15 brokers. In this way, we can tune the cluster size by simply redirecting the traffic to a different cluster. Inside each Kafka cluster, we create one topic dedicated to the stress testing. The number of partitions in that topic is basically 10 times I think it's 10 times of the number of brokers. And of course, they're evenly distributed among all the brokers so that we have an even workload inside the cluster. We are having much more partitions than the broker, so that we don't necessarily bump into the bottleneck where we're having too few partitions. And another thing I'd like to mention is that the clients and the brokers are in 2 different regions in United States, so that the network latency is quite high. And as a result, the limits that we obtained can be applicable to the virtually all the use cases that we have in Dropbox infrastructure. So now about the algorithm. At the top level, it's the algorithm is very simple. If you perform sufficiently many stress testing, exert sufficiently many different traffic patterns on the Kafka cluster, you can simply observe the effect on the cluster, whether the traffic is overloading the cluster or whether they're not. You plot all those points, and if you draw the boundary between the traffic that overloads the cluster and the ones that are safe, then that boundary becomes the limit of your cluster. In terms of how do you characterize a particular traffic pattern, as you can imagine, there might be many factors. For instance, message per second, size of each message, how many clients do you have, even the content of the message can play a part in here. For our testing, we chose the 2 most prominent factors here. One is the message per second, and the other is the size of each message. So naturally, these are the very easy candidate, and together they can, if you multiply them together, they basically form the throughput of that particular traffic. And another thing I'd like to mention is that the message content that we're using is fully randomized, so that the optimization that can be brought by the compression is minimized, and that again help us to obtain a much more conservative throughput limit. And the auto tester works by examining a series of different message sizes from low value to a high value. For each different message size, it will start by generating the traffic with a very high MPS, or message per second. And the traffic will definitely overload the cluster. And then it performs a binary search on the possible MPS values. In the end, it will stop at the pair of the values, and the pair is sufficiently, and the values are sufficiently close, and yet the lower value is safe to Kafka, and the higher value is overloads the cluster. Then the lower value will be chosen by us to be the limit, a throughput limit on this particular Kafka cluster for this particular message size. And then we repeat the process for all the other different message sizes. And if we do this in sufficiently many times, we will be able to plot a fairly accurate boundary for the throughput limit.
Question?
Yes.
How do you define the boundary? What is safe and what is overloaded?
That's a good question. So there are a few indicators that we used to determine that. I think the biggest one, the most useful one to us is whether there is a ISR change or ISR expansion or shrink. So that means there are brokers falling behind and then catching on. That means that they are under great stress. And the other indicators that we're using is like CPU utilization and things like that. Good question. Next is, here's the result that we had for the 3 clusters. As you can see that these data points fall nicely on hyperbolic curves, which means that we have pretty consistent throughput over a wide range of different message sizes. And based on this result, we concluded that in our infrastructure, the throughput limit is basically around 60 megabytes per second for each broker, and this can scale up linearly. And again, I want to just mention that this is based on our infrastructure, our hardware, and again, this is a very conservative limit because we are, the network latency is very high, and also the message content is fully randomized. We actually tried different type of message content where the content is simply one character repeating itself. As you can imagine, the compression ratio in that case is extremely high. And in that case, we actually observed much, much higher throughput limit in the experiment. Basically, that's because the network I/O and the disk I/O becomes much less of an bottleneck. All right, next I'm going to talk about the scaling in the asynchronous data pipeline. So basically, we re-architected the data pipeline. Instead of having the goscribe aggregator producing to a single Kafka cluster, now it produces message to a collection of shard clusters. It basically produces messages in the round-robin fashion. This greatly helped us to improve the availability. Let's suppose if one topic in one shard becomes unavailable, then the goscribe aggregator simply switches to the other shard cluster without us even noticing the temporal unavailability. Similarly, for each shard cluster, if it needs to be replaced or needs some offline maintenance, we can just safely take it offline without impacting the whole pipeline in any way. Besides this, it also provides other benefits. For instance, we can scale up and cope with the organic traffic growth by introducing new shard clusters instead of increasing the size of a single cluster indefinitely. Again, that help us to have a much more manageable cluster size. It's going to be much easier to maintain the cluster. The maintenance time on the cluster with the bounded size is going to be much more manageable, and thus we'll end up with a more reliable system. Next is for the synchronous use cases, we implemented this emergency failover mechanism. It is very straightforward. In every major data center, we have prepared one backup Kafka cluster, and we also embedded a switch in all the Kafka producer and consumer clients. When the serving Kafka cluster becomes unavailable, we flip the switch, and the traffic will be failed over to the backup cluster. When we do the transition, it will be rate limited so that we make sure that we don't set up all the connection at once, because we already know that's a recipe for disaster. So with that, we are able to respond to the failure in a more meaningful and faster way. But still, we consider this as less than ideal because as you can probably see, it still involves manual intervention here. And we will still need to coordinate with our users to make the switch. This can be a particular difficult issue in the cluster where it is multi-tenancy. And in that case, we need to work with multiple users from multiple teams to do the transition, and that alone can be a painful process. That is why we consider this as the phase 1 solution. And for phase 2, it's going to be dynamic failover, which is going to be built on top of the queue service that I'm going to talk next. So we've been at Dropbox, we've been thinking about the future of Kafka as a service, and so we want to improve the availability and availability and reliability of the system, and we also want to minimize the overhead of maintenance additionally, we want to be able to support more use cases, support more requirements in a much easier way. So with those goals in mind, we built this queue service in the past year. Conceptually, it's very simple. It's simply a proxy in front of Kafka. We are basically isolating Kafka physical clusters from our users. It's very simple, but I think the bigger question here is that why we're doing this. There's obviously trade-off here. We're adding an extra layer here. The latency is going to be higher, and we're hiding away Kafka from the users, meaning that we are inevitably also hiding away useful Kafka features from the user. Then why we're doing this? Well, we have a few reasons. First of all, we really want to have real-time traffic control. So one biggest reason, like I have previously mentioned, we want to be able to dynamic failover and we want to take control completely by ourselves. And it will be very easy if we can control we can be the gateway for all the Kafka traffic. Additionally, there are benefits, other benefits. For instance, we can impose a quota system, a fine-grained quota system. For instance, we can assign quota to different teams, and we can assign quota for different topics. That means we may be able to better support situation of multi-tenancy, and we can save resource in that regard. Another big reason here is that we want to enforce safe traffic pattern. Like I previously mentioned, having all the connection established at the same time is a recipe for disaster. And it is very hard to ask our users to stick to that principle. And it's going to be much easier if instead we control all the Kafka clients. And another reason here is that with its queue service as a platform, it's going to be very easy for us to customize the behavior, the traffic pattern, and also integrate things with our in-house technology. So like the quota system I mentioned, we have internally something called scoreboard that is used to maintain this maintain this quota. And also there's this rate limiting. We can do global rate limiting. We can do rate limiting by coupled with quota, things like that. And also fine-grained authentication and rich monitoring, things like that. Here's the topology of the queue service. This won't be a surprise because this is what you would expect from the typical proxy. We have the deployment of queue service in every major data center, and we have developed a thin client that mimics Kafka native clients. And the clients talk to our queue service through gRPC, which is the Inter-Process Communication Protocol adopted by Dropbox. The clients will look for local queue service. If it's there, talk to it. Otherwise, fall back to a global queue service. For those of you who are interested, the queue service internally features of modular design for its internal architecture. It is actually agnostic to the queuing backend, and we have abstracted away the queuing backend with the concept of plugin. So in order to support a new backend, you simply implement a produce plugin that knows how to produce to that backend, and also a consume consume plugin that knows how to consume from it. And the queue service has a very small kernel. We call that the common foundation logic. The only thing it does is to route the traffic between user requests to the corresponding plugin. And because the kernel is very small, it is very easy to understand and easy to maintain. And we can, and additionally, it is highly extensible. By that, I can give you an example. For instance, as you know, the plugin is just an interface, and that means any plugin that because all the plugins conform to the same interface, we can easily combine them together and form more to support more sophisticated use cases. For instance, let's say we want all the messages to a certain topic to be simultaneously double produced to another Kafka cluster. In that case, we can simply combine two produce plugin together, and then we have a double produce plugin. Similarly, we can have another type of composite plugin that can produce to a collection of shard clusters. Or similarly, we can implement dynamic failover. And because of the nice abstraction, we're able to support those sophisticated traffic patterns very easily. With this queue service as the base layer platform, we're able to do quite a number of interesting and valuable things. First of all, like we have mentioned multiple times, dynamic failover has been something that we've been dreaming of for quite a long time. And next is that next something is we've been prototyping. That is, we want to transparently back up Kafka data in cold storage. And that recall that Richie said we're making this policy of data retention for 1 to 3 days. And actually there are valid use cases that want much longer data retention. And what do we do for those use cases? We can simply store the data in cold storage whenever the user wants to rewind or rewind to the historical data, maybe because of the outage. We can simply backfill the data from the cold storage. It economically checks out. Finally, we want to build higher level features on top of the queue service platform. For instance, one thing we're considering is to build the PubSub service on top of it. All right, so automated stress testing, sharding, and emergency failover, and finally queue service. These are the major projects that we did in the past year that helped us combat all those challenges of reliability and also paved way for the future of Kafka as a service at Dropbox. That basically concludes our presentation. What are your questions?
Any questions?
Hello, okay. For the emergency failover case, how do you transfer consumer offsets?
So for the consumer offsets, we do not transfer it. So this is one of the challenges of emergency failure, and that's why I wanted to queue service to set the data is not lost. The idea is just high availability. So even if there is an emergency failure, you move the data to the producers, like the producers are moved to the new clusters. On the consumer side, there are two options. One is your consumer is, your cluster is completely dead and you cannot consume it all. So then you completely switch on your consumer and start consuming from the new one. The data is lost. If we can recover the cluster, we will pull the data back into the new consumer. The other option is if your cluster is still partially working, then you can stop the producers, but your consumers can still consume from the old cluster with a higher latency. And when the whole data is drained, then we switch on the consumers. So it's like a step-by-step process. And as I said, it's like, as Pang said, it's a manual process. You have to determine what is the situation right now and fail over accordingly.
And another question was for the queue service, is your consumer pull-based protocol? So in other words, do you have to solve the partition assignment issue? Because if you had a consumer instance, it needs to connect into the right queue service instance that's holding that partition because you need to read from Kafka.
For the queue service, the consumer lives inside the server, and our user will just hold a lightweight thin consumer that actually it's a gRPC client and that talks to our server.
But there's a discovery mechanism because each of their instances needs to know which queue service server actually holds your partition.
Actually, it doesn't have to because it's a For consumers, we're using a gRPC streaming protocol, and the initial request sent from the consumer actually established the consumer object inside the server, and then it just keep communicating.
And do you solve the partition fan-out issue? So if you have a user who wants 1 million instances and you only have 4 partition topic, how do you do that?
Sorry, can you repeat the question?
How do you handle? So if a user client of your queue service wants more instances than you have partitions, how does each of their instances connect to the correct queue service? In other words, your queue service consumer is not fully stateless. Is it fully stateless?
It is fully stateless.
So if any new client, queue service consumer client comes up, it just hits a random queue service server?
Yep.
And then that spins up a consumer client?
The consumer will provide the group ID and also which topics they want to consume from. Does that make sense? And the queue service will hold the collection of consumer objects.
So you still have the limitation of the number of active queue service consumer clients is limited by the number of partitions.
Yeah.
Okay.
You mentioned that you can auto-scale partition count for recovery or for preventive actions. If you auto-scale up, what is your system or protocol currently to deal with once the load is reduced again? Or do you just leave it?
We cannot reduce. That is one of the, I think, yeah, we cannot reduce the number of partitions. And that's why we do not automatically do it. We create a bot and still ask the on-call to see whether it's a real partition increase, because there are times when we know, okay, the traffic increased only for 1 hour. We don't have, we can still, balance it and then not increase the partitions. You cannot. This is for emergency failover?
Yes. Yeah, so essentially you can only increase so if it has to happen, then how do you decrease the number of brokers? You just switch to a different cluster? I mean, at some point, if you increase the clusters and the emergency goes away.
So I think you guys are talking about different things. He's talking about the number of partitions. So in a partitions for a cluster, you cannot increase. If you are cluster level increasing, decreasing, that you can do, yeah.
Yeah, maybe I can also add up to the question here. Actually, in the community now, we are having the KIP for basically having this tiered storage, and it's driven by the community, and actually it's also aligns with Dropbox goal to have this cold storage as well. And with the tier storage, you actually can afford to really have a large number of partitions and move them around with a very small operational overhead. So basically, you can just when you do the capacity planning, you can just design with the highest peak of the traffic, and you can stick with that number of partitions. You don't need to expand or shrink anymore. That is like one option you can consider once you have the tier storage in place.
When's that going to happen?
Well, that is still ongoing in community. So I think the KIP is being discussed. So we have an expectation that it will be voted soon, maybe in this release cycle.
Cool, thanks.
Any more questions? Okay, let's thank our speakers again. Thank you.